Okay, gang, let's get started. Here we go. Class number 33. So a couple of things going on. I just returned quiz number 4. Some of you gave me the related rates quiz on Wednesday. They are sitting in my office. I have not touched them. For those of you that did not give me that related rates quiz Wednesday, throw it into the green folder for me right now. Also due right now is the data project, so the regression one, so throw that in the green folder as well. Coming up on Wednesday, the Rainbow Project will be due. Friday is our review for test number 3, which is happening Monday. 1 week from today is our third test, and that test is going to be on everything since test number 2. Okay, so today is the last day of new material. 2 days more of new material for the test. Today is families of curves, and then Wednesday is L'Hopital's rule. L'Hopital's rule. Any questions on that calendar? Okay, then let's jump in on page 37. In this class, we use calculus to understand the behavior of a family of functions, and we find a member of a family with specified properties. Isn't this perfect for Thanksgiving and family? We're talking about families, right? It's fantastic. All right. Here we go. A formula such as f of x equals ax squared plus bx plus c describes a family of functions. It is an infinite collection of functions. In this case, we know the word to describe the graph. What word describes the graph of those things? It is a polynomial, but what's the name of the graph where it's a degree 2? Parabola, right? This is a parabola. And so this is a whole family of parabola, an infinite family of parabolas. You imagine, like different values of a make it like go up or down or thinner or wider, or, like we can change a, b, and c and get a whole slew of parabolas. A, b, and c are called parameters, and this family is a 3-parameter family, a, b, and c, okay? So here's what we're going to do. We are going to find a member of this family of parabolas that has some specific properties. Here we go. We'll find a parabola of that form that passes through the point 1, comma 4, and whose tangent lines at x equals -1 and x equals 5 have slopes 6 and -2 respectively. I'm going to draw a picture, although you don't need a picture at all to do these kinds of problems. It says it's supposed to go through the point 1, 4. Okay, let's find that 1 and then 4. So it's up here. Now, we're not saying that that's the vertex. We're just saying the parabola hits that point. And then it says the tangent line at x equals -1 has a slope of 6. Okay, so at -1, the slope is 6. Do I know that the parabola hits down here at -1 on the x-axis? No, it might be up here, right? Or it might be like way down here. I don't know. There's like a whole vertical column, and the parabola hits one spot on that vertical column. But wherever it hits, it's supposed to have a slope of, except those are not 6s. Those are -6s. So wherever it hits is supposed to be really steep uphill, someplace way up here or down there or somewhere in between. But I don't know. And then the same deal at at 5, it's supposed to have a slope of -2, so let's go over to 5, so someplace out here, and the slope is supposed to be -2, so kind of steep and going downhill. Maybe it's there, maybe it's way down here, maybe it's up there. So trying to make a parabola that like satisfies all 3 of those things, it's not trivial. Can you look at this and sort of imagine a parabola that does those 3 things? Like it's really steep over there to the left, steep uphill, going through the blue point, and then, downhill not as steep. Is this parabola going to be opening up or down? It's got to open down, I think. I think it's on its way up as it hits one of these orange things. I don't know where it's going to hit. I'll say like it hits here someplace. Then it hits that point. At some point, it's got to turn around. I don't know. Maybe it turns around up there, and then it's like just starting to come back down. Like it's not quite as steep here, and then it gets like steeper over there. Something like that. But it's hard. So let's see if we can do some algebra and calculus to actually find the equation of the one perfect thing that satisfies all those conditions. Okay, first it hits the point 1, 4. That's not calculus. That just means plug in 1 for the x's and 4 for the y. So 4 equals a times 1 squared plus b times 1 plus c. Or 4 equals a plus b plus c. Okay, there's nothing else to do with that. It's one equation with 3 unknowns. It will only help us after we know the values of 2 of those variables, right? So maybe like we'll figure out a and b, and this will help us find c. something like that. So we'll put that aside. We got tangent lines. Okay, I know that tangent lines have to do with, they have slopes, and I know that slope of the tangent line is the derivative. So that's the part where I say, okay, I better take a derivative of the original function. It might look intimidating. There's 4 letters in this thing, A, B, C, and X, but only one of them is the variable. What is it? X. So everything else is constant. So A times X squared, it is not a product rule. It's just a number getting multiplied by a derivative, and the derivative of X squared is 2X. I'll put the 2 in the front and the X at the back. Plus, what's the derivative of BX? It's just B, it's like 5X, it's just 5. And then what's the derivative of that plus C? 0, it's constant. Okay, so there's my derivative. And then it says, if you look at the tangent line at -1, the slope is 6. What am I going to do with my green thing here? F prime of 6 equals something. F prime of -1 equals 6. That's it. If you plug -1 in for the x, the slope is 6, but that's the output for the tangent, for the derivative. So we just plug in. 6 is for sure equal to f prime of -1. And let's go ahead and do the same thing with the other tangent line we're given. It says that when x is 5, the slope is -2. -2 equals f prime of 5. Good. Okay, and so let's go ahead and use our green now. I can plug -1 in for those green x's. So I get 2a times -1 plus b times -1, right? I didn't quite have enough space over there, so I'm going to recopy. A bx. Thank you for catching that. Another intentional mistake on my part. And I'm such a good actor that like you think that I didn't do it on purpose. All right, so I get rid of that. I get rid of that. Okay, how's that look? Good. Okay, so we plug in and then we'll just start simplifying. So this becomes 6 equals, that's just a -2a plus b. That's one equation there. And then we'll go to the second blue equation and we'll plug what number in for the green x? 5. So 2a times 5 plus the b. 10a plus b. Okay. The calculus is all done. The rest of this problem is straight up algebra. We've got 3 unknowns, a, b, and c. And we now have 3 equations with those unknowns in them. The 2 blue ones we just wrote, and what color is the other one? It's that black one in the top right. 3 equations, 3 unknowns. That's the magic number that's going to make this work. So now we call on our algebra skills, trying to solve this system of equations, the 3 equations and the 3 unknowns. I'm going to focus on the 2 blue ones because they're simpler. They don't have all 3 letters in them. You could do the substitution technique where you solve one equation for b and plug into the other equation, substitute into the other. That's totally good. It turns out because the b's perfectly matched, like it's one b in both, if you subtract these equations, what happens to those b's? The b's disappear. And so that's the simplest way, only in this particular case. So I will subtract a bottom equation minus top equation is what I'm doing. No, let's go the other way, top minus bottom. So 6 minus -2, that's 8, equals -2a minus 10a, that's -12a. And then the b's cancel when I subtract. So that was top minus bottom. Divide both sides by -12 and reduce. So a is -2/3. And then you plug that value of a into either of the blue equations, and then we can figure out b. Let's plug into the top equation. 6 equals -2 times the a, which we just discovered is -2/3, plus the b. Okay, so 6 is equal to, that's a 4/3 plus the b, and then subtract the 4/3, so 18 minus 4, that's 14/3. From the blue equations, we subtracted, I'll write it here in orange, so we did the top equation minus the bottom equation. And we did that intentionally because it happens that the b's would cancel perfectly. It would have been a little bit tougher if one of them was like 3b and the other was just b. Yeah. Okay, so that's a and b, and then how do we find c? Plug back into that top equation, right? We know a plus b plus c is 4, so put it all together back in the top. So we'll come back over here. So we know 4 is equal to a plus b plus c. 4 is equal to a was negative 2/3 plus b, that's 14/3 plus c, which we're about to find. Yeah, turns out c is 0. Okay, so that means our final answer, f of x equals, so it was ax squared. That is negative 2/3 x squared plus bx plus 14/3 x, and then plus 0, which I won't write. Okay, so that's it. And what I want to do is, let's see if we can do this in less than 60 seconds. We'll give it a shot. I'd really like to see what GeoGebra has to say about that particular parabola and check and make sure that the 3 conditions hold. So all I'm going to do is graph this equation, negative 2/3 x squared plus 14/3. Let's make this a little bit bigger for you guys. Okay, font size, good. All right, so that equation was f of x equals negative 2/3 x squared plus 14/3 x, yeah? Okay, so let's drag this down just a little bit so we can see the whole thing. All right, so one point that was supposed to be on the parabola was what? Was it? 1,4. Okay, so hey, look, there it is on my parabola. Excellent. And then we've got tangent lines. So I forget, one of these things is my tangent line thing. Is it in here? Oh, it's over here. Here we go. Right, tangents. Okay, so I think we should just have to pick the curve and a point. I'm doing this in the wrong order. I'm going to put a dot on there, and then I can take this point and I can move it anywhere, but it's always tethered to the parabola. And then what I want is the tangent line at that point. So tangent line, so I think we pick the point and then we pick the curve. Boom. Okay, so there's my tangent line at a generic point, which follows the point as I move around. There were 2 particular x's I was interested in. What were they? Okay, so I'm going to go to -1. And right now what I'm looking at is on the left-hand side here, this guy right here. And so I found -1, and what's the slope of that tangent line? 5.99. Well, this is not quite here. We'll be a little more precise here. Okay, yeah, so like I'm not quite at -1. I don't know how close I can get to -1, but I'm feeling pretty good that that we've got a slope of 6 at that spot, right? And then what was the other x? 5, and the slope is supposed to be -2. Okay, so I'm just looking at the left-hand side, trying to get close to 5. And is that slope real close to -2? Yeah, so we found our winner. I think we had a pretty good sense that this is what it was going to look like at the start, but now we've precisely found it. Okay, so before you jump into the activity, who cares? I mean, like, we're just playing with parabolas, right? Who in their right mind would ever try to find a parabola with those 3 conditions? Okay, probably nobody other than like some nerdy math teacher, but But the idea here is that we have control over these functions, and this is sort of a powerful idea, is that you can make a function that satisfies certain conditions, and maybe these aren't the most interesting conditions in the world, but this process is an important one, right? Finding a function that satisfies certain criteria, we now have the ability to do this with a lot of control. Okay, so jump into the activity. Number one is there, and then in number two, you are going to conclude the surge function activity from earlier this semester. So it will remind you of what you're doing there.